So let's look at another problem. I think this one is from chapter 12, I think, in the book. It's one of the worked example 12.1. I think, let me confirm, I think it's chapter 12, yeah, chapter 12, example 12.1. So let's try to find sublimation pressure of water vapor at this temperature using data available in our steam table. So sublimation is literally moving from solid to gas direct. That's the definition. So let me just try to show you what this problem actually doing. Remember your phase diagram. So I think we have gas here, we have solid here, and we have liquid here. So we already know that here, okay, this is pressure, this is temperature. Already know that we wanted to here to be negative 60 degrees Celsius, so we're trying to find what is our P for this sublimation, right? So that's what this thing is doing. So we're going to employ this Clapeyron equation, because that's what it does, give us the relationship of these slopes. So this equation is literally derived from your what do you call this one, your free energy equations, your Gibbs energy equation, from the fact that the free energy on is the same for both sides. So you can actually just take G saying is the same for solid and gas, and then you can actually even say the slope is also the same. You can do dt, and then from that I think you can learn to the equation they call it in your book 12.7. So let me just write it here because it was given to us. I think it's look like this. HFG. Okay, I probably copied the wrong equation, but yeah, I think it's like this. dp p is equals to integral from 1 to 2, integral from 1 to 2 of ig dt t squared r is equals to I think I have dt, everything's fine. So if I integrate both sides here, this side will have ln p2 all over p1 is equals to, if I integrate here, I'll have hig all over that big R, then different in temperatures all over products of the temperatures. This is just your math, moving that to there. Okay, so we're trying to find what is happening given that one, but we're going to use information that is given from our available steam table. Let's go to our steam table. So what else we notice, that if you talk about water at this temperature, it should be solid. So we're going to look at the steam table for the iced part. So let's find our steam table. Where is it? We're going to look for ice. Scroll around the page, we'll find it just now. Superheated water, contains superheated compressed liquid ice. Yeah, that's what we're looking for. So we're looking for negative we're looking for for 40, right? So let's deal some stuff. Let's deal this column. I don't know, I'm taking all of it, but safe than sorry. So I already told you where I got this value, and let me just I stole this one from my steam table. So Let's try to convert the temperature we have into Kelvin. So we started with, they gave us negative 40 temperature. It was called negative 40. I think if I take that, remember that we got that thing from, we got this piece from our table, what do you call it? From steam table, iced table A8. So our T2, after converting, we're going to have T33 Kelvin. I'm using Kelvins. Then T1, I'm going to have 213 Kelvin. So the information that we have from a steam table is for 40. That's why we're using as our what do you call this, our second temperature, right? T1 is the one that we started with, and this one is one that we're getting here. So we're trying to go find what is happening here at negative 60, given that we know what is happening there. So let's continue. So let's plug and play, because that's what it is. Now we have lean, forgive me for writing lean like that. P2 is the one that we're getting from our steam table, right? Because it's associated with this one. Is it? Then our P2 is going to be, you can check my steam table there. It's going to be this guy here. That's 0. It's going to be 0. I'm getting it from here. It's going to be 0.01285 close. And then P1 is what we wish to find. Okay. This guy also we're getting exactly from that guy again. Did I, oh, yes, it's here. Still from the steam table. Then I think we saw it was 285, no, 283. I think that was 5. No, 2838.3 all over. R is a constant. It's going to be 0.4615. Okay, let me remove these. We don't need them here for now. We can continue. Then difference in the temperatures, T2 is 233 minus 213 all over 213 by 233. And then you compute. If I put all of this side in the calculator, it yields I think 2.478, and this side I will have let me just lean both sides. So I'll just have, if I mean e both sides, if I e this one, I'll have 0.0128 all over P1, and then you can solve for P1 here, just basic your math, then it will be 0.1077 kPa. So already interpolated, we got the answer here. So that's what, yeah, that's all. So the motivation, you just plug it. The thing is, just get your Clapeyron equation here to do things for you. And remember, bring back your steam table. You see your steam table is giving you your T2. You already have your T1, of which wasn't a problem. That's what you wish to find for. Yeah. So literally what you're doing here, this is your T1. You know something around T2. Then you use that data to interpolate for the other one, if interpolating is a good word. So yeah, so this is literally all about what is going on this PT diagram, phase diagram. Thank you for watching.